Okay, thank you very much. Thank you for the invitation. I'm sorry I couldn't be there in person with you. I had everything planned. I had flights booked, but a bit of an emergency situation came up. So I have to be with you virtually, and I hope to join you some other time. So what I'd like to talk about today is a topic that is aligned with the theme of the workshop, which is Bayesian inverse problems, and in particular, the use of deep neural networks that are parsimonious in some sense, that capture in some sense, the geometry of the map from parameters to observables to construct surrogate models that are then used to accelerate Bayesian inversion, and in particular, optimal experimental design, which is a very challenging topic since it is an optimization problem wrapped around a Bayesian inverse problem. And as if the Bayesian inverse problem governed by large-scale PDEs, as if that were not difficult enough, OED adds an extra layer. So this is joint work with Tom O'Leary-Roseberry, Ki Wu, Peng Chen, who is with you, and Umberto Villa. They are either current or former members of the group, and Peng is with you, so you can ask him questions afterwards and find out more if you'd like. All right, so I'd like to start off with a few examples of problems we're working on in the group that motivate this sort of work. The first is subduction earthquakes, subduction zone earthquakes, and in particular, the Cascadia subduction zone. So this is off the coast of the Pacific Northwest. And the idea is that the two plates that are meeting there, the Juan de Fuca plate and the North American plate, and the continental plate is typically thicker and stiffer. So the oceanic plate is subducting underneath as they're pushed towards each other. They're locked at the moment, but the strain is accumulating, and at some point there will be an earthquake in which the overriding plate is pushed above, lifting up a column of water, generating tsunamis. The tsunami will head towards shore, or may head, depending on the dynamics of the rupture, may head towards the shore, and with wave heights 15 meters, maybe even 20 meters, as we saw in Japan in 2011 in Tohoku earthquake. So you'd like an early warning system, which means you have to solve an inverse problem rapidly to estimate the ground motion along the subduction zone. That's in this region here. This is a proposal. This system does not yet exist, but you see this cable system here with the yellow dots representing locations of pressure transducers, which will measure the acoustic waves generated by the ground motion, so the acoustic waves in the ocean. And these are then inverted to obtain the ground motion everywhere. And then that way we can predict the effect of the moving seabed, and then forward predict using a shallow water equation. So that's the forward prediction is through the shallow water equations that will predict the wave height at the coast. The inverse problem itself is solved with the acoustic wave equation coupled to gravity waves at the surface. So it's a coupled system of PDEs, and that has to be done in real time. So to do this in real time, which means you have about 20 minutes, 30 minutes, but of course you don't want to use all that time. You want early warning. So really you'd like in seconds to do the inverse problem and then make predictions on where the wave height will be largest. You cannot evacuate the entire Northwest, Pacific Northwest. So you'd like to predict where the wave height will be largest. Okay, so we need surrogate models of the parameter-to-observable map. And ultimately, we need optimal experimental design to tell us where the best location, this is $1 billion proposed program, which actually probably costs 2 or 3 times as much to instrument the seabed with, connected by fiber. Okay, so that's one example problem. Here's another one that we're working on. This has to do with block copolymer systems. These are systems of interacting polymers that combine to form nanostructures, which can be used in semiconductors and other nanoelectronics. Depending on how they are externally controlled, you can get different patterns that form. And these are actual photo micrographs of these different patterns. And so the idea with directed self-assembly, they self-assemble on their own into these patterns, and they form, length scales in, the tens, and even, sub 10 is an aim, nanometers. So the idea is that with directed self-assembly, you can induce them to form different patterns that would be of use to you. And the direction can be through a chemical substrate at the base. They could be through a laser that's applied externally, a thermal heat source. And the idea is we have models for these. That's the non-local Cahn-Hilliard equation. There's a non-local term, and the rest looks like classical Cahn-Hilliard, which governs the phase separation. But the idea is the model itself is deficient. So we'd like to assimilate data in real time and then use that to control the laser and push the structure towards one that is desired. And so we, typically can absorb, in this case with X-ray scattering in real time, or we'd like to do this in real time, and reconstruct the state of the system, perhaps their parameters as well. We'd like to reconstruct that govern the different terms in the Cahn-Hilliard energy, and then solve in real time. So of course, if this is going to be done in real time, you have a Cahn-Hilliard equation, you cannot use the full order model. So you'd like to use a reduced model, or some kind of surrogate. Okay, so we need a surrogate from, in this case, the parameters are the state variables, so the state to observable. The observables tend to be these images that are captured from the scattered X-rays. But here's the third problem. I'll give an example of this later. This is an inverse problem for the friction at the base of the Antarctic ice sheet. So the ice is flowing under gravity into the ocean. Satellite observations over the past several decades have indicated acceleration of the flow, particularly in areas like the Western Antarctic ice sheet, where alone 5 to 7 meters of sea level rise are locked into the ice in this region. And the acceleration of the last several decades, we need an explanation for it. It's thought to be the warming of the ocean and the way the ocean interacts with the ice shelf. The ice shelf is the part of the ice sheet that is floating on the water as the ice flows off of land onto the water. So the floating part, the ocean has been warming and thinning that out. And as the ice shelves, which I'm not showing in this picture here, the picture just shows the ice sheets, but the ice shelf is as those collapse, and occasionally we hear in the news of a large collapse event, as they collapse, they have a buttressing effect. They keep the ice on land from flowing into the ocean. So you move that and the ice flows faster. That's the mechanism that is postulated. We'd like to model this. The major uncertainty is what resistance is there to the flow at the base of the ice sheet. We call it a friction. It's not really a friction. It's a coefficient in a Robin boundary condition that takes a linear combination of a free slip and a no slip boundary condition. So that parameter there is a field everywhere at the base of the ice sheet. That's what's shown in the upper right picture here. So these are observations. This is surface velocities from INSAR satellites. So these are observed surface velocities. You see very fast flowing ice streams in certain areas. Those are kilometers per year, 3, 4, 5 kilometers per year. We solve the inverse problem. We go backwards through the flow equations, which are the Stokes, not Navier-Stokes. It's a creeping flow. So it's the Stokes equations, but with nonlinear rheology, highly nonlinear rheology, and it's a shear thinning fluid in particular. And you see these fast flowing, you see this reduced resistance to flow captured by these red regions. So this is the inverse solution. And this is the Laplace approximation. This shows the standard deviation field. So this is the standard deviation field here. You can see much lower standard deviation near the ocean where the ice is flowing fastest. That's where we learn the most about the friction at the base of the ice sheet from the surface velocities. And so now what is now this is not a real-time problem. In fact, we have a few years to affect policy, but it is a very large-scale, complex forward model. If we're going to be doing the full Bayesian solution, which we haven't done, we've only done the Laplace approximation already. That involved about 100,000 forward solves. So we need a surrogate model to be able to do the 10 to the 6th, order 10 to the 6th samples that you need to fully explore the posterior. If you're doing it using Markov chain Monte Carlo, but other methods, there's a conservation of pain. So we'd like to have a surrogate that maps the parameter field, which is, it's a field at the base of the ice about 1,000,000 degrees of freedom, to the surface velocities, which are, also about 1,000,000 degrees of freedom. The mesh is adaptive throughout this three-dimensional domain, but, roughly about the same. So 1,000,000 to 1,000,000 map, and that has to be executed many times. So as I said, we need a surrogate, but importantly also, we need a surrogate for optimal experimental design. There's an opportunity to place ice cores, which give a temperature distribution through the thickness. So this is coupled mass, momentum, and energy, the balance of those three. The temperature affects the constitutive law. So you can put some ice cores, you can drill them. They're very expensive in these remote regions of Antarctica. You go down several kilometers, you can capture the temperature through the column. That's an excellent observable on top of the existing, surface velocity, but it's very expensive. So again, we need surrogates. Here's the last example I'll show, and that is a well. There's a well here that is in desert regions. In the west of the U.S., we're experiencing severe droughts, and aquifers are we tend to have overproduction of aquifers, leading to a potential collapse in the pressure, in which case you may have collapse of the pore space, in which case the aquifer cannot be recharged when the rains come. So that's a danger if you overproduce it. And so we have an inverse problem to solve, which tells us something about the subsurface properties of an aquifer. And then optimal experimental design is where do we put new wells to observe and or control by injecting fluid. And then ultimately, we'd like to solve an optimal control problem under uncertainty. So we need surrogate models for all of those. This shows, the top picture shows the elastic deformation. So how do we solve an inverse problem? You just have a single well that doesn't give you much information. We can add some additional wells, it's very expensive. But we can also use the surface displacement, again, using synthetic aperture radar. This shows the vertical, this is a radar image from the INSAR. And you can see there's a large subsidence bowl over here. Because the well in the red star there, as you extract the fluid that lowers the pressure, that leads to elastic deformation of the earth. So this is the subsidence, the negative displacement. And there's actually a bowl there, and you can see there's a shape, as it turns out, of increased deformation. And it turns out, when we solve the inverse problem, coupled, this is a poroelasticity equation, coupled subsurface flow with elastic deformation. What we end up inferring, because of the surface signature, we infer that there's a region of higher permeability there, which leads to large displacements in that region. And so we'd like to solve, we have solved this in the Bayesian context. I'm not showing you the Bayesian solution, but this one was compact enough that we could do full, Bayesian Markov chain Monte Carlo, accelerated by second order information, Hessian information, through a generalized preconditioned Frank-Nicholson scheme. So that we were able to do with sufficient computing time on a coarse-ish 3D poroelastic mesh. But the optimal experimental design is out of the question, because then the Bayesian inverse problem has to be solved repeatedly to determine where the best wells are. Okay, I'll skip the last example. So I don't think you need convincing that we need surrogate models of parameter-to-observable maps in order to do Bayesian inverse problems, optimal experimental design, and ultimately optimal control and decision-making under uncertainty that you get from these Bayesian inverse problem solutions that give you models that are appropriate for decision-making. Everyone at this workshop, I'm sure, is convinced of this, but okay, I did want to share with you some of the problems we're working on. So they all have a common structure. The parameter field typically is a discretized infinite dimensional parameter field, initial conditions, material properties, boundary conditions, sources. I think we gave examples of all of those except for the geometry. You could have geometry as well. The outputs are also high dimensional. In the case of the INSAR, we had a surface velocity field, so it was effectively an infinite dimensional field. The radar resolution, the satellite resolution is 5-meter grid spacing. So effectively infinite dimensional on an Antarctic continent that is thousands of kilometers in extent. So, but in other problems where you have discrete sensors, okay, it's still high dimensional, you're measuring in time. So the output dimension can be very high dimensional. Input dimension is definitely high dimensional. We have expensive mathematical models, whether it's poroelasticity or or shear thinning, non-Newtonian flow of the ice, or coupled acoustic gravity wave propagation, and the need to infer model parameters and compute optimal controls under uncertainty. And in some cases, we need to compute this in real time. I put real time in quotes. Real time simply means, it's a balance of the computational effort needed with the timescales needed to make decisions. If those conspire such that the timescales are shorter than what you can compute, that becomes real time. So we demand surrogate models in all of these cases. Okay, so the challenge of surrogate models, everyone knows. There's the curse of dimensionality. If you're trying to approximate a function, parameter to observable map F with one based on n samples, the error scales like n to the minus s over d, where s is the smoothness, and d is the dimension that you're in very high dimensions. So that means that it can be hopeless. The convergence rate deteriorates exponentially with dimension. We have a number of available surrogate methods, Gaussian processes, radial basis functions, etc. Typically, these suffer from the curse of dimensionality, though some things can be done. And the key thing that one does in all these cases is to recognize that d itself is not the ambient dimension, the apparent dimension, but if we could exploit some sort of effective dimension, so smaller d, and if we can assure that it is dimension independent, or in the cases where we can't prove it, at least like the ones that I showed you, numerically, we can observe decay of, let's say, eigenvalues of the Jacobian of the parameter to observable map, the singular values of the parameter to observable map. If they decay sufficiently rapidly, then the problem is governed effectively in lower dimensions. If we can exploit that, then we can build an approximation in lower dimensions. So that's what we're going to do today. We're going to do it with neural networks. So parametric neural networks, we are trying to approximate a map Q of M, where M here is the symbol that we're using for the model parameters, be they initial conditions, boundary conditions, source terms, etc. So these are equipped with a probability distribution nu, and these are mapped to outputs Q. The map is governed by the forward problem, which symbolically here is R of U comma M is 0. So U is the state variables, and U depends on M through the solution of the forward problem. So we need, the key thing in this whole business is we need accurate surrogates with limited training data. So of course, if we could afford 10 to the 6th solutions of the forward problem to train a surrogate model, then there's no point in using the surrogate because we could afford 10 to the 6th samples. So we have to get by with order 100, order thousands, perhaps, depending on the problem. So we looked to neural networks motivated by recent theoretical work. There's work, for example, by Christoph and collaborators, Jacob Zeck, who I think is there with you, and Christoph is there with you, on dimension-independent exponential convergence rates for example, ReLU networks. So we'd like to construct surrogates that exploit the intrinsic low-dimensional structure of the map and use that to come up with parsimonious networks. And the key idea is if we can exploit this low dimensions, then we're building a network in low dimensions, and we won't have many weights, so we don't need much training data. All right, so here's basically in one slide the whole story. The input dimension, so we have some high dimensional input, which is discretization of typically an infinite dimensional field. And then we're looking for a linear basis that will construct a subspace in which we have a high quality approximation of these inputs. The way this is done is through what might be called a vector form of active subspace or an expectation of the Gauss-Newton Hessian. This is the Jacobian of the parameter to observable map. So Jacobian transpose Jacobian, that's the Gauss-Newton Hessian. We compute its expectation over parameter space, and then we do a truncated spectral decomposition. So V are the eigenvectors. This is a tall thin matrix, and we have the eigenvalues, capital lambda. And the hope is that R is small. So this is the dimension R here, and the coordinates that you see that feed into the network after you get to this first layer, the reduced coordinates are the coordinates in this low-dimensional subspace. And that's what the neural network sees. And we'll talk about the neural network in a second. Now, what about the output? So the output, so again, we have a high-dimensional output. This is the observation space. It could be finite dimensional, it could be discretized infinite dimensional, but often it's high-dimensional. So we could do the complement of this, which is Jacobian transpose. So that's the Gauss-Newton Hessian in the data space and compute its expectation over parameter space and do a truncated spectral decomposition. But to first order, this is equivalent. So this is can be viewed as a POD. So it's Q transpose, the output vector Q transpose, its expectation over parameter space. This is cheaper to do to first order the same thing. So we do a truncated spectral decomposition there as well. And so this reduced dimension subspace, this is given by these vectors span that subspace. So the eigenvectors. Now we typically, we'd like to use a ResNet for various reasons in this low dimensional representation. And the ResNet requires a constant breadth. So we choose simply the larger of these two. And if we were using the Gauss-Newton Hessian in the data space, those two would be the same. But since we're using POD, we may have to choose the larger of the two. Okay, so in between we put a nonlinear ResNet. Now, because the a linear subspace, it generally is going to be conservative. It's going to overestimate the reduced dimension. For example, you can just think of the Rosenbach function. So this is an example. It's in 2 dimensions, so it's a thought experiment. But the classic banana-shaped Rosenbach function. So we look at this and we say, oh well, this is a one-dimensional problem. There's an important dimension at any point in parameter space. That's the important direction. The problem, though, is if we have a linear subspace, and in particular, if you just compute this Gauss-Newton Hessian expectation over parameter space, at each of these points, the important direction is changing. So in the end, you conclude that both dimensions, the full dimension, are important, and that's an overestimate. Now, generally, what this will do is if you use this device to find a reduced dimensional subspace, you are using Occam's razor to eliminate all the fat, all of essentially the null space of this expected Hessian. That takes away all of the degrees of the directions in parameter space that are irrelevant, in which the parameters don't affect the observables universally. So regardless of where you are in parameter space, and that tends to be infinite dimensional. For these kinds of problems, certainly for elliptic and parabolic inverse problems, and we can even argue, I can argue later for certain classes of hyperbolic problems, you have an infinite, for example, for propagating waves, if you're trying to infer the material properties, you cannot see anything less than half a wavelength, for example. So everything less than half a wavelength is in the null space of this Gauss-Newton Hessian, regardless of where you are in parameter space. And that's infinite dimensional. So you cut away all of that null space. Now you're left with something that may be a bit too large. So you'd like to do a further dimension reduction. And that's where the low rank ResNet comes in. And so the ResNet is, there's an identity part of the map here, and then you're acting on the input to the layer, and you have a low dimensional. Let me switch back to the pointer. So then you have a reduced basis representation. So the weights that you invert, that you train in the neural network, there's a low dimensional map. The activation function is in a further low dimension, and then there's another extension from the low dimension back up to the larger dimension. So we have the n dimension input, we have the r dimension after the linear subspace has been constructed, and then we have a further k, this dimension here is k reduction that gives us effectively a nonlinear manifold representation. That's given by the neural network, so it has to be trained, and admittedly, that's a non-convex problem, so it's challenging and the usual issues with neural networks. But in practice, we find it works quite well, as you'll see in the examples. Okay, so I'm going to skip, I made this claim we're going to do a truncated spectral decomposition of this expected Gauss-Newton Hessian, and some of you are shaking your heads like, well, how are you going to compute that? That's a real mess. But the idea is very simply, I'll just say it in one slide. is, we're going to do Monte Carlo approximation of this expectation, and then we'll use a matrix-free method, in particular randomized SVD, to construct the low rank approximation, the truncated spectral decomposition. It has this nice property that you only have to form the actions of the Gauss-Newton Hessian in random directions. So this is a linearized forward solve, with a Jacobian acting on the random direction. This is a linearized adjoint solve of the Jacobian transpose acting on a vector. Those can all be done. You can work them out at infinite dimensional level and work and just do them in a software like Phoenix. It's easy to do. Writing down just weak forms, and so it's quite nice. So these are actually the version of SVD we use. Randomized SVD uses two passes, so it's actually two R linearized PDE systems that we have to solve, and then we have to do that NMC times the number of Monte Carlo times. But all of these two NR, they have the same operators, the same PDE, linearized PDE operator. So we can exploit, for example, direct solvers, we just factor once, and even iterative solvers, we construct a high quality precondition that we reuse over and over. So the only cost we feel is the N, is the Monte Carlo, and then really the R, arguably, you just do it once. If you construct a algebraic multi-grid preconditioner, that's quite expensive, but then you amortize it over all of these R. What R is the effective rank. It's the rank. It's the effective rank, which for many problems, as I said, is low dimensional and independent of the parameter dimension. It's finite dimensional. And for example, the elliptic inverse problems, the eigenvalues decay algebraically, for parabolic they decay exponentially, and for hyperbolic problems, of course, it depends on the problem, but like the scattering of waves, as I argued, you can have lower dimensional. Now, that's not true universally. We'll talk about that. For example, with increasing Reynolds number, increasing frequency of wave propagation, that R will grow and grow. And so the hope is then that the K, the inner neural network dimension, will capture things in lower dimension. But there are things a bit more open, certainly in the hyperbolic case. Okay, so that's the basic idea, and in the end, we capture the important information in the expected information gain from the data can be written in terms of the log of 1 plus the eigenvalues. So when the eigenvalues are small relative to 1, then we can truncate there. And in particular, I'll give you an example. So this Antarctica example. These are the eigenvalues of the Gauss-Newton Hessian, and this is actually for two meshes, one with about 400,000 parameters, one refined with about 1.2 million parameters. The spectra lie on top of each other, which indicates that the data provide a finite amount of information about the parameters that's captured through this Gauss-Newton Hessian. If you refine further and increase the dimension of the parameter space, you will not extract any more information from the data. And this is showing you, so these, again, these are the eigenvalues. We truncate when we get, when we're sufficiently below 1, because of that criterion we saw earlier, log of 1 plus lambda I. So lambda I is small, we've captured all the information. And this shows you some of the eigenvectors. And you can see they're highly non-homogeneous, they're highly heterogeneous. And as you get into, this is the 4,000th eigenvector. These are limits about what the data can tell us. And you can see that, you get this high heterogeneity along these ice streams. For example, we're learning quite a bit, but we learn more in the direction of the ice flow. And you can see a high order mode in that direction. Across the ice stream, we learn less information because the higher velocities in light stream direction. Essentially, they're telling us more about what's happening at the subsurface. Okay, but the lower modes tend to be smoother, which is typical of many of these problems. All right, so what can we say about the error in this representation? Assuming you have the exact map in the reduced dimension, so this is just the linear projection, then the difference between the true parameter observable map and the projection, the projected representation in expectation is limited by, this is an SVD type of result, by the truncation in the input dimension and the truncation in the output dimension. So these are the trailing eigenvalues. And so when these eigenvalues decay rapidly, we can get away with a much smaller representation. All right, and then now we add, as I said, the nonlinear ResNet, which is a low rank ResNet in which this is the previous layer, the input from the previous layer. So there are weights and biases. The weights themselves, this is like, as we said, is a thin, tall, thin matrix here that we, or short and wide matrix of weights that we solve for in the training, in the optimization problem, and the same thing on the other side. This one is tall and thin. So the reduced weights. And the nice thing about ResNets is, many of you know, we can add these things incrementally, layer by layer, until we reach an overfitting situation. So there's an adaptive construction, and that in our examples tends to do much better. Now we add in, so that's assuming the map, that's capturing the map exactly in the subspaces, and that's the error that's committed, but now you're going to replace it with this ResNet. So now you have additional error, first of all, because you're solving an empirical risk optimization problem, and so number of samples that are used, the training samples, there's statistical error due to those, and then there's the fact that you're solving a non-convex optimization problem, so there can be network error in training, and that adds as well. So overall, you get a bound that has these four sources, and the first two are certainly controllable.
Can I, Omar?
Yeah.
Just ask a quick question. Isn't there also an error coming from the way you compute these these dominant directions via Monte Carlo? I mean, you randomly computed these, right? So why does it show up?
Yeah, I don't have the expression here, but that's absolutely right. So the error goes something like this. The error between the true, I'll just use the symbol H, the true Hessian, or just Jacobian transpose Jacobian, minus let's say the approximated, the approximation. So that's this one. So that error in the Frobenius norm with randomized SVD is for either case, the input and the output, because of this randomized truncated decomposition. So this is the standard SVD type error. So these are the trailing eigenvalues, r plus 1 to n. But then there's a prefactor. And this prefactor, I forget the exact form, but essentially it can be made close to 1 with a bit of oversampling. So I said you need r samples where r is the rank. Turns out you need a few more extra. And so someone there might remember the form, but it looks something like r plus some oversampling. Let's call it S. I forget the expression, but anyway, the expression tends to 1 as the oversample. And you don't need much. For Antarctica, for r equals 4,000 or 5,000, we oversample by about 20 or 30. And that is controllable. And that gets it down to a constant factor of maybe 5.
You say 2R, right? You choose always 2R random directions. Was it this oversampling? I mean, or was it?
Okay. No, the 2 comes from a double pass version of the algorithm, which is more accurate. There is a single pass version where you just do R Hessian vector products, and that's all you need. Yeah, we do the 2R, which is you can think of it as like an iterative refinement. So it's 2R plus some 2 oversampling. So basically, instead of R, we use R plus 10 or 20. It's a small number, typically, really quite small. So order, so basically order R in the end. Yeah, that's a good question. So there is a little bit of error from that, but that's controllable. And this is the one that this is the error that keeps me up at night. Okay, thank you for the question. So then, all right, my screen is a little bit frozen. I can go in this direction. Okay, here we go. All right, so here's an example. This is a Helmholtz problem. So it's 16,000 parameter dimension. So yeah, not massive, but large enough to expose the challenges. We're going to observe the scattered wave field at 200 observers along the top surface. So this model is a seismic inversion experiment. Soft plus activation. The inner layer in the nonlinear resonance is only 4. So actually that's really quite small. What we're going to see is a 16,000 through the linear subspace. We're going to reduce it, depends on the experiment, to 64 or 48 or some cases 100. Then we'll have 512 testing, 128 validation, and we'll compute the accuracy in the standard way that it's done. So generalization accuracy over unseen data. And we're going to compare a projected ResNet, where the projection is not done through this Gauss-Newton Hessian. People say, oh, that's too expensive. It's intrusive. We require adjoints of the code. In some cases, adjoints are not even well defined. So why not just reduce by the prior? Use the prior as a reduction. So we call that the KLE, Carhoonen-Loew network, KLE expansion network. We'll also compare with a naive, no one's going to do this, but that's the baseline, a naive network where you go from the high dimensions of the input to the high dimensions of the output, and then a truncated dense network where we go from high dimensions, because you might ask, why not let the neural network do all the dimension reduction? Why do this linear subspace first? You have to do these offline computations. We can avoid those, throw everything into the neural network and let it rip. So how well does this work? Let's see. And then of course, so it's a Helmholtz equation. We're inverting for the log wave slowness. That's the M field. That's the, not the wave velocity, but the wave slowness. And that's so it's a field, and we have some, some boundary conditions and free surface and PML boundary conditions, and we use a Maturin covariance to represent the parameter distribution, the prior parameter distribution. This is just a sample of the prior, and this shows a typical wave field. So it's not a high frequency problem. You can see certain half a dozen wavelengths, and these are the observation locations here. And for the OED problem, we're going to subselect these. Okay, so we're going to choose where to place the sensors. From among the 200, we're going to choose 20 or 30 or 40, depending on the experiment. This shows a typical result. So these results have the accuracy, the generalization accuracy on the vertical axis, and the number of training data on the horizontal axis. We care about being in the left part of the regime. We want high accuracy for low number of training data. Again, we can't afford to solve the PDE many times. And what we see with this adaptive projected ResNet, it has a small number of weights because of this double reduction, the linear subspace reduction, and then the ResNet has its own low rank reduction. And so you achieve high accuracy pretty quickly, with relatively small number of training data. I mean, this problem, if you want to do the Bayesian inverse problem, you're going to do 100,000 or 10 to the 6th or a million samples to get an accurate posterior. If it costs you 1,000 forward solves to train the surrogate, then you win overall. And I'll show examples where we win by 3 orders of magnitude. This had 64, so the R equals 64. That's the linear subspace dimension. 5 ResNet, and as I said, K equals 4 is the low rank ResNet dimension. Okay, so this is what the method I talked about does. But for example, if you use a KLE, so the best case with the KLE, using the prior covariance, doing a Carhoonen-Loew expansion of that, capturing the same dimension, 64, you see the number of weights are the same in both cases, you do much poorer. Well, of course, you haven't taken into account the parameter-to-observable map. The geometry of that map does not factor into the reduction, so it's whatever the prior tells you is the reduced dimension. That's what you end up with. Okay, so maybe we didn't need to do an experiment to tell us that, but since people do use priors as dimension reduction, that's what you get. This is a comparison now with a truncated dense. So this is just let the network figure things out. Don't do this initial Jacobian, expected Jacobian. And what you get is not bad, but you still have a gap here the gap remains in the generalization accuracy, whereas this, what I talked about, you get over 90% fairly early. So basically the truncated, of course, the full is actually in this case not so bad. Well, it's quite bad if you have not enough information. This green curve. So this is this full dense, just let the network do the dimension reduction. The truncated dense is where you prescribe R equals 48, and then the neural network weights are just determined by the training. Okay, okay, skip that. So here is an application to Navier-Stokes flow around a wing. Maybe let me skip this one to get to the OED. But so this has been done for some fairly complex problems. Navier-Stokes is a turbulent flow, but we're using a turbulence model, Reynolds average Navier-Stokes, which is typically what's used for design. And we're trying to find the optimal shape. The ResNet is this projected ResNet is used as a representation, not of the shape variable to objective function. So we want to solve an optimization problem to minimize the drag subject to balance on the lift and the moment coefficient and volume. This is actually we learn the optimization solution. That's another talk. But just to say we've used it for some 3D.
Omar, may I ask you a question on this one?
Yeah.
What is your data?
Okay, so thank you, Homan. This one, the input is the Reynolds number and these two parameters that are inputs to the design problem. So this is typically this is what a designer would want to specify the design problem and then rapidly solve to explore the design space. So this is not a forward problem that we're learning, the map. This is actually the optimization problem. So the inputs to the optimization problem are these 4 parameters. So it's low dimensional. We don't have to do dimension reduction on the input. So we don't do that. Then the training data is actually the 3D shape optimization problem using Navier-Stokes Reynolds average German's model. So that's a full-blown code that takes hours and hours to run, hours just on a cluster for one 3D. And then the output is the optimal shape. And that one is relatively high dimensional. I mean, considering Navier-Stokes, it's 200 control points that determine the shape of the wing at a certain number of locations. The airfoil shape along the wing. Yeah, so that's the data are actually runs of a CFD-based design optimization. Okay, so we can get into that later. Yeah, thanks for the question. And so in this case, also this strategy, again, we didn't have to do anything on the input, but we certainly had to reduce the output. It turns out that the output dimension here was quite small. I'm not showing you what it was, but I think I have it somewhere. No, I don't have it here. But anyway, we achieved a 99.98% accurate representation with 10 to the 7th speed up using not many training data, training, a few hundred to get up to this is the L2, this is the generalization accuracy in the optimum shape. But what we care about is the drag coefficient, the objective function. So that was even higher, 99.98%. With a few hundred runs of a CFD code. Okay, so then I want to show you in the last couple of minutes optimal experimental design. So this is a workshop on Bayesian inverse problems. I don't have to talk about Bayesian inverse problems. So it's a standard setup. And just to say that we would like to solve the OED problem. OED is it's an optimization loop around a Bayesian inverse problem. And so what is the objective? There are many different criteria one could use, different utility functions. The utility function we use is the expectation over the data of the Kullback-Leibler divergence between the prior and the posterior. Okay, so what is the Kullback-Leibler divergence? That's given by the expectation of the log of the posterior over the prior with respect to the posterior. So this is the double whammy, the double intractability of OED. If you're doing it in this full-blown way, you have this high-dimensional integral with respect to the posterior, and then another expectation with respect to the data. And if you do this using a standard sort of brute force double loop Monte Carlo, it's hopeless. You end up with number of Monte Carlo samples. The product of the two samples, the inner and the outer loop. So it's out of the question. We need some kind of surrogate. And so we're going to compute a surrogate of the parameter-to-observable map. So in this case, this is the forward map. We're going to do the same strategy we talked about, illustrated with the Helmholtz equation. So a parameter-to-observable map, we're going to capture that by a surrogate. And now, how do we do the optimal? What is the experimental design? Well, we introduce a design matrix W such that Wij is 1 if the ith sensor is placed at the jth candidate sensor location. So we choose a finite number of discrete candidate sensor locations, and we're trying to find a subset of those. And then we can introduce this weighting matrix into the parameter-to-observable map and into the noise. And so the W is exposed now. So our utility function will depend on W. The question is utility function. We cannot use double loop Monte Carlo for that. So instead, well, I'll skip this. There's some manipulations that we do, but in the end, we use the surrogate representation of the parameter-to-observable map to accelerate the samples. Okay, so once constructed, we never touch the PDE again, as you do with any surrogate. So here's a typical result. Again, we have these 200 possible locations. We'd like to sub-select 20 or 30 or 40, depending on the problem. You'll see, and I'll show you just two sample results. Let's focus on this picture lower left here. The blue curve shows the expected information gain on the vertical axis as a function of the number of outer loop samples. So we're fixing the number of inner samples at 60,000. The blue is the reference solution. We could have done more, but this is the reference solution in blue here, which is brute force double loop Monte Carlo. Then the orange is this DipNet, this derivative informed projected. So the thing I've been talking about, this neural network I've been talking about, this one uses 6,000 forward solves of the PDE to train the neural network surrogate, uses 6,000, and that's it, it fixes them. So it is cheaper than the blue, much cheaper, in order of it's 60,000 inner samples multiplied by, let's say, 100, if you look here, 100 outer samples. So that's really 6 million PDE solves. So versus 6,000, so 3 orders of magnitude reduction, and it's as accurate as it's of the same order of accuracy. Whereas the simple double loop Monte Carlo, in which we restrict the Monte Carlo sampling to the number of PDE solves that were used to train the neural network. So the green and the orange have the same training cost, or the same cost, and you can see that there's a big gap here between the two. So that's for the expected information gain. And now, what is the effect on the solution itself of the OED problem if we use this as a proxy, as a surrogate, this representation? So what we have here, let's look at this one. This is the relative error I'll get to the solution of the OED problem in a second. This is the relative error in the objective function. So this is this expected information gain, expected KL divergence. What you see is the surrogate, the neural network surrogate, the error, the distribution of the error. These are for random designs. So if I choose how many? 200 random designs, you see the distribution of the error with the surrogate, and you see it with the simple double loop Monte Carlo. This is the one that says it's the same cost, same number of PDE solves, but I use Monte Carlo sampling. And you can see the gap between them opens up as I increase the number of sensors. So as you get to higher and higher dimensional OED space, as your decision space where to put the sensors that gets bigger, you open up a larger gap. And then finally, if we compute the optimal solution using the surrogate, now how we compute the optimal solution, that's a whole other discussion. That's using a greedy algorithm that places and removes sensors in a greedy sort of way. But the net result of these magenta X's, that is what you achieve with this greedy algorithm plus the surrogate. The distribution here, again, this is 200 random designs. That is using the ground truth double loop Monte Carlo with the 6 million overall samples. And so you see the distribution here. So at the upper end of the range, you get close to the optimum, but you get a distribution. You don't do as well. Of course, the higher, this is expected information gain. So we'd like to place the sensors to maximize the expected information gain, to gain as much information from the parameters. So as you go up here, that's better. So this suggests that using this, even though in the Helmholtz case, the accuracy is about 92% or so, I think the best case we got up to close to 95%. But even if that's the case, this surrogate can still accelerate and give you a reasonable, a solution certainly better than doing a brute force double loop Monte Carlo. And then, I mean, you can see 200 random samples here. Okay, so I'll stop here. This summary, I don't need to go through. It's basically just repeating everything I said, that there is a typically low information dimension that you can capture using a linear subspace first, followed by using a neural network to reduce further. You can think of it as a nonlinear manifold. This is you end up with a parsimonious network that has fewer weights to train, which means less training data that's needed. And this can be used in Bayesian inversion optimal experimental design. However, and there's always a however, as I said, the framework is predicated on the viability of the low rank approximation to get you that first reduction. If we didn't do that first linear subspace reduction, if we just let the network, figure everything out, let the K dimension be the reduction, the experience is that the optimizer, whether you're using the standard first order stochastic gradient descent atom stuff, or we have our own custom second order Hessian accelerated stochastic Newton type methods, either of those you use, you get into trouble. The network is, as you saw in those examples, you're worse off. It's the non-convexity, the high dimension, massive number of weights. If you try to build a neural network representation using those large number of weights, you just get poor solutions. So we like to use that first reduction, but that does require the R is small relative to N. And a number of problems we've shown this over the years for many different problems. You can see a list of those there. And every one of those has, even Peng can tell you about, even with a COVID infectious disease spread model, that thing has, he had 1,000 parameters in his model, but even that had an effective low dimension in the tens. But it doesn't hold universally. We know this. The information dimension grows with increasing frequency in wave propagation, with increasing advection in advection-dominated flows, Reynolds number, Peclet number, et cetera. So what can be done in those cases? That's open. It's an interesting research question. A global low rank isn't the right thing to do, which immediately leads you to think in terms of H matrices. So it's a hierarchical low rank, off diagonals are low rank in a hierarchical way. We've had some success in using those to approximate Hessians of nonlinear inverse problems, but even those start to deteriorate. The ordering is very important for those, and for like these wave propagation problems, for example, it's not clear what the ordering should be because the waves are bouncing everywhere. And translation invariant approximations, product convolution approximations, again, some success with those, but it's definitely not, it's still an open problem. And then the last thing we're working on, and this is, we'll have a paper on the archive soon, where we use derivatives to try. So in other words, we bring in derivatives in the training, not just the function values, because we're going to use the surrogate for solving optimization problems. Ultimately, if it's going to be derivative enhanced, derivative accelerated MCMC or Stein variational methods or optimal transport methods that use Jacobian information, we'd like the surrogate to be derivative ready. It should be H1 accurate, not just L2. So that's a whole interesting thing in and of itself, because the Jacobian is very high dimensional. So again, you use low rank Jacobians. Okay, so there's some software that's available. Thank you very much. And I've gone a little bit over. I apologize for that. Again, I'm sorry that I can't be with you. And in fact, I have to run off to a retreat for my department retreat is today. So I'm sorry, Roman, I'll miss your talk, but I'll watch the recording and I'm sure I'll learn very much from it. So thank you very much.